Hi, this is ET370, and this is lecture 2, part 2. Okay, and so we previously covered Zener diodes, and now we're going to step back to regular diodes, but we're going to go over this ideal diode assumption, and we'll talk about the number of possible combinations of when you have diodes in your system. And it's actually 2 to the n. You'll see this again when we talk about binary, because diodes have two states, right? Either off or on, reverse bias, forward bias. And just like a bit has 1 or 0, so you'll see this to the end reoccur. And we'll go over two simple examples to kind of wrap it up. All right. So the ideal diode assumption, well, if you recall from our previous lecture that we had something like this for the IV curve, right? So we had voltage and current. Okay, and so after a certain amount of forward voltage, you get current. Well, in the ideal diode assumption, we're going to assume that there's no forward voltage. You just have this straight vertical line, right? So it's either on or off, right? So no forward voltage, no breakdown. Okay, this is going to be your ideal diode assumption. So you don't get any breakdown here. Okay. Um, and so what do we have here? Notice you have still the VD and ID drawn correctly according to the diode. And when it's on, what you need to do is you will assume that the voltage is 0, but you need to check if the current is positive. Okay, that makes sense. If it's off, or if you're going to assume it's off, you will assume that the current is 0, but you will need to check and verify if the voltage is negative. And how do you do these two things? Well, you'll have to like plug into your circuit and then analyze your circuit and verify these two things are true. If that's true, then you can safely make these assumptions whether it was on or off. Okay, and hopefully in those examples it'll highlight these statements here. All right, so let's look at possible combinations of diodes. Okay, for a circuit with n number of diodes, there are 2 to the n possible combinations. So if there's, for example, one diode, 2 to the n is the same as 2 to the 1, which means there's 2 possible states, on or off. Straightforward. And now if there's 2 diodes, what do we have? 2 to the n, 2 to the 2, which is 4. And what do you have? On, off, off, right? So those would be your 4. N equals 3 or 3 diodes, now you're going to have 8. 2 to the 3 is 8. So very simple little rule. Based on the number of diodes, you would know how many different combinations that state could operate in, right? Okay, so let's do a simple example with this ideal diode assumption, right? We have one diode here, which means we have only 2 states that it could be in, right? 2 to the 1 is just 2. Now, what should we assume? Well, we got a voltage here, a resistance. We see this current. Yeah, it's probably on, right? And what we're going to do, though, is just go the dumb way and just check off. Let's just assume it was off, and we better see that this guy gets violated, right? This little condition here is not going to be correct. So the other question is solve for the current, right? So once you've figured out what the correct state of this diode is, then solve the current. Well, we're going to probably assume this is ideal, this is short, so you're probably just going to have Ohm's law. Okay, so let's tackle this using these new ideal diode assumption rules. Okay, so we're going to assume ideal, right? So assume ideal. And what do we have if we assume that it's off? Well, you got to be careful here. You got to write down the voltage here, right? And the current still. And I'm going to redraw it with an open circuit. A lot of students forget to do this, right? I want you to redraw it with an open circuit, and now we can analyze. Well, when it's off, you will assume already that it's 0, but we need to check, is this voltage in fact negative? If this voltage comes out positive, we made the wrong guess. Okay, so let's look at this. In this case, if I is 0, this VR by Ohm's law is going to be 0, right? And you can see by KVL straight up, 10 volts is going to be equal to this voltage of the diode. That's going to relate to a incorrect assumption here of off, right? And you can see by Ohm's law, yep, 0, KVL, you can do the simple 10 minus VR minus VD equals 0, or VD equals 10 volts. That's positive, which means our assumption is wrong. So we will try on. Good. So let's go to the next one. If it's on, what are we going to do? We are going to assume that it is a short. And now we got to check. We will assume that it's 0 volts across here. but we will need to check, did we get positive current? If we got positive current, that is the correct state, and then we can answer the question, which is, what is the current in this correct state? Okay, so let's go and see what's going on here. We got 10 volts, 2 ohms still. I correctly redrew the short and then the same reference. Notice in this problem and this problem, I drew the same reference. That did not change. It just changed. I just changed the guess. Okay. Now in this case, if this is a short, I can just do a simple nodal Ohm's law. ID equals 10 minus 0 over 2, which is positive 5 amps. Yes, that means I guessed correctly, right? So it meets the criteria for on. And hey, look at this. I've actually already solved for the answer of the question, and that is ID is 5. Okay, 5 amps. Very simple example. Let's do a more complicated one. Okay, so look at this kind of crazy example. What do we have? We have 2 diodes, which means 2 to the n, 2 to the 2 means there's 4 total states. Now, if we get lucky and guess the correct state, one of the 4 right off the bat, we don't have to check the other ones, right? But if we go about it naively, we might find that, okay, this was wrong, and then finally get to it, okay? What do we notice here? We see a little arrow, right? When we see this arrow, it means current can flow. And really what this is saying is I'm just gonna redraw this so that it's a little easier for everyone to understand. It means this: you have a resistor here, diode, sure, everything's happy. And you really have this plus or minus Vs. That's actually, these are equivalent here. Okay, so both of these drawings are the same thing. And when you see all these grounds, actually just means a wire is connected. Okay, so this drawing here is the same as that drawing, so don't be confused, right? So in other words, the node voltage at that point is Vs, okay, and current can flow. Okay, so they tell us that this is 15 volts, and they give us all the numbers. So this is 5 kilo ohms, 10 kilo ohms, 5 kilo ohms, 10 kilo ohms. And the question is, what is I and what is V, assuming ideal diodes, right? So we need to first pick the correct states. And how do we pick the correct states? Well, it's kind of a little bit of intuition. You got to kind of guess, and then you got to check, right? That's all it is really guess from your intuition, check. Once you've checked and you've verified this is on or off or whatever it happens to be, then you go and don't forget to answer this question, this I and this V. Okay. So we got all our combinations. So diode 1, diode 2, they could be off, 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 on, off, or on, on. These are the 4 different combinations for this guy, right? And so again, we're going to check which state is consistent with ideal diode assumptions and solve for I and B once we have it. All right. So let's just make an arbitrary guess here. So we're going to assume that they're both off, right? This is probably wrong, but let's guess that they're both off. And what we have to do is we have to redraw it with it off, and we have to put the proper voltage and current directions. Now, we don't really care about the current directions in this case because it's off, so we know the current's 0, but the voltage polarity totally matters. Look at this, positive here, here, and minus sign on the cathode. Same for this one, the minus sign on the cathode. Don't get that messed up. All right, so then we have ID equals 0, and we need to verify if that voltage is actually negative, because this would only be an open circuit if we had a reverse bias situation, right? So we need to check this one right here. If this ends up being a positive number, well, that's incorrect. Okay, so we have VD is negative, VD is 1, 2 are negative. Okay, so that means let's look at what's going on here. This is 0 current, right? Because there's no closed circuit. So that means this actually node voltage here is 0, okay? Looks like there's no current here, okay, right? Because this is open circuit. So that means the node voltage at this point is actually Vs. And the node voltage here is at 0. I think you can already see that VD1 is actually going to be Vs by KVL, right? Yep, VD1 is equal to Vs minus 0, which is 15 volts. Already broken. We can move on. Case 1 is already invalidated. Okay, good. Let's go to case 2. So case 2, what do we have? Off and on, all right? Okay, so we're just naively going through this. Maybe, if you're doing a problem, you can hone in on the correct one, but we're just gonna go 1 through here, 1, 2, 3, 4, and just see which one pings as a correct one. Okay, so again, I'm assuming that this is off and this is on, right? I'm redrawing carefully the polarities and current direction. So in this case, I didn't draw the voltage because I'm assuming it's on. I already know the voltage and the second one is 0. And this one, I didn't draw the current because I know the current is 0, but I did draw the voltage polarity. And what do I have to verify? I need to verify if this is negative and this is positive. Okay. Again, don't get that messed up. All right. So let's see, what can we do to double check? Well, again, no currents flowing through R1. So that means this node must be VS. All right. If I find that this V here is actually less than VS, I know that this is actually a incorrect assumption, right? Because if this is 15 minus, let's say 10, this will be a positive voltage. Okay, so how would we find V, right? Could we find this? Well, what do we have? We have a current path that goes through here. It looks like I could combine this. Look at these two, they're in parallel. So I could do the parallel combination. I could actually do a voltage divider to solve for that V. That's pretty straightforward. Okay, so let's do that. Okay, so what's the parallel combination of R3 and R4? Well, that's pretty straightforward. We can just use our 250 formulas. R3, R4 over R3 plus R4 ends up being 3.3 kilo ohms. So this combination. And then I can do a voltage divider. So this is 3.3, and then this R2 is 10. Okay, and so what do I get? I get 3.75 using our voltage divider. Do I have the signs correct? Yep, positive. This would be positive, sure. Okay, so this is 3.7 volts here, and this is 15 over here. I think you can already see that this is invalidated, right? So by KVL, yep, 11.25 breaks the assumption. Case 2, boom, not valid. Okay, so we can move on to the next one. Let's go to 3 and see if we get it correct. So I hope these little examples, these naive examples, are helping solidify how to analyze which state is correct for this problem. Okay, so let's go to 3, on and off. And again, note, I didn't draw the voltage polarity because for the shorter case, I know it's 0, right? But I did draw the correct current direction. And then for this one, I didn't draw the current direction because I actually did because I need to solve for I eventually. But I did put the voltage to positive and minus to follow the direction of the diode symbol. Okay. So what do we have to do to figure out if this was a correct guess? This needs to be positive and this needs to be negative. All right. Okay, how can we confirm these things are true? We have 15 volts here. We know all these resistances. I can already see this ID1 is probably going to be positive. Look at this. You have R1, R4, and a voltage across it. We can do a nodal Ohm's law on this series R1, R4, and I can already tell this is going to work. That's going to be positive. Okay. If I get this current, then I could actually, by Ohm's law, get this voltage. Is that right? ID1 times R4 is going to be this V. Good. So I can get that voltage. And look at this V prime here. If I know this voltage and if I know V prime, I would be able to solve for VD2. Okay. But how would I get V prime? V prime, oh, look at this, 2 resistors in series voltage divider. So I think we have a strategy on how to solve for V prime V, which will, by KVL, will give us VD2. We want this to be negative, and we want this to be positive. Okay, so let's tackle it, put some numbers on it. Okay, so we'll do a nodal Ohm's law in here. So it's Vs minus 0 over the series of R1 plus R4. Good, I put series here. And I end up getting 1 milliamp, which is positive. Yay, this supports our assumption. Okay, so diode 1 is okay. What's the next step? So by KVL, I know that this VD2 is V prime minus V. Good, V prime minus V. Good. And then let's go to the next step here. By the voltage divider principle, yep, I can say that V prime is Vs times R3 over the sum, which ends up being 5. Okay, so that's 5 volts. And what's this? By Ohm's law, this is just ID1 times R4, which ends up being 10 volts. Yes. So if that's 10 volts, that's 5 volts. This by KVL is going to be negative 5 volts. And that's negative, which matches our assumption. So that means state 3 was actually the correct one, where this is on and this is off. Now we got to go and finish and solve the problem. And what's the problem? The problem was actually solve for I and V. So what is this I and this V? Well, if we chose this and this is verified to be correct, I is actually 0 amps. And what is V? Well, we actually already solved it. V in this case is 10 volts. Okay, So I hope this example highlights how to just use this simple ideal diode assumption and make sure you do this guess and check procedure correctly. Okay, I hope you learned something, and see you in the next one.